Hello, everyone. I'm Supraja, like Morley said, and thank you for the introduction. Now, in the cloud, we all know that computation is rapidly moving to specialized accelerators. And with that, confidential computing, which has mostly been processor-bound so far, needs to also be enabled on these specialized accelerators. Now, you might say that NVIDIA's H100 does exactly that. And yes, it does. So let's consider that case, because people are looking at enabling these confidential computing solutions on these devices. So if we have a processor and a device, both with confidential computing support, and we attach them together, the question is this secure? And right now, yes, because by default, these devices simply cannot access any protected memory on these processors, which obviously this is secure, but clearly not functional. So to make this functional, we could use an encrypted channel over shared memory. But this would involve a whole bunch of software-based encryption, decryption cycles, and memory copies, which is obviously slow. And as you can see here, we look at NVIDIA's numbers, for example. NVIDIA's H100 GPUs, when connected over PCIe with link speeds that can reach up to 256 Gbps bandwidth, can barely get to 4 Gbps with this bounce buffer setup because of the slow software-based encryption. Now, for devices where performance is so critical, clearly we should do better than this. And another approach is to make these devices first-class principal in confidential compute settings and allow them to directly access this processor memory. And this is what we enable in ACAI. So ACAI is the first system that allows connecting PCIe devices to these CCA-based processors. We take a principled approach where we extend CCA's invariants carefully to ensure device security, and we build a concrete design to portray our compatibility and performance of our design. Now, before I dive into any more details, we need a little bit of background on our CCA. CCA instantiates 4 worlds that software can execute in, and in the most privileged root world, CCA executes a trusted firmware. And to isolate these worlds from each other, CCA introduces a memory filter on all of its processing elements that are programmed by this trusted firmware. CCA also enables the creation of realm VMs, and to isolate the realm VMs from each other, it deploys a thin layer of trusted software in the realm world called the realm management monitor. This realm management monitor, or RMM, programs stage 2 translation tables that isolates the realm VMs from each other. Now, I understand that this was a lot of information on one slide, but there are 2 key points that we need to remember from this slide. First, that these memory filters programmed by the trusted firmware isolates the worlds in CCA, and second, that the stage 2 translation tables programmed by the RMM isolates the realm VMs from each other. Now, that said, in CCA, we want to give these devices direct access to processor memory. And the way we do this is using CCA's optional device assignment extensions. But as I will show in the rest of this talk, we need to be careful while using this extension to ensure security. First, we need to decide how these devices and when these devices are connected to these realm VMs. And there are many ways to do this. First, we can time share these devices between the different realm VMs, or we can attach and detach these devices dynamically during the realm VM's lifecycle, also known as hot plugging, usually. And if these devices have multi-tenancy support, you could also share them spatially between different realm VMs. In CCA, we looked at current cloud deployments and found that, and as a first step, we basically attached this device to one VM throughout its lifecycle. Now, once we've attached this device, there are several attacks that are possible. If we naively give these devices access to this protected realm VM memory, then any device can get access to this memory, essentially defeating CCA security. So this is not good. So we need to ensure that these device accesses to memory are isolated to their respective realm VMs. And this brings us to my first invariant. To ensure this invariant, we observe that there is an SMMU that intercepts all memory accesses from these devices. And this SMMU, just like the cores, has stage 2 translation and these memory filters. So like CCA, we use the trusted firmware and the RMM to program these stage 2 translation tables and the memory filters. And this gives us our invariant. But there is a problem here. The SMMU usually is programmed by the hypervisor. And if we allow this hypervisor to go and configure this SMMU directly, then any protection that we got using these memory filters and translation tables are useless. So to stop this, we move the SMMU to the root world, the configuration to the root world, and we use the trusted firmware to stop such misconfigurations. Now with that, the hypervisor can still mount mapping attacks. So by default in CCA, it enforces an invariant that ensures one-to-one mapping between the intermediate physical addresses and host physical addresses for the realm VMs. And we maintain this for the devices as well. So in this example, you can see that both the realm VM and the device can access physical address 1 through different intermediate physical addresses, but that's fine. This still ensures this invariant, right? Now what the hypervisor can do is it can manipulate the device's translation tables to something that looks like this. Now this, while it still guarantees this invariant, this holds, but can lead to split view attacks. So what has now happened is the device is accessing physical address 2, while the realm VM accesses physical address 1, and they both think they're accessing the same memory. This is clearly bad. So in ACAI, we strengthen this invariant to ensure that the device and the realm VM see the same view. To do this, we just tie the RMM stage 2 translation tables together, and this basically gives us this property. Now that was about mapping attacks. The hypervisor can still, memory mapping attacks, and the hypervisor can still mount device mapping attacks. Say we have this case where we have a victim realm VM connected to a device and a co-resident attacker realm VM. What the hypervisor can now do is attach the same device to the attacker's realm VM as well. What that effectively means is now this device has access to both the victim's memory and the attacker's memory. So through this device, the attacker's realm VM can mount cross-VM attacks. This is bad, and to stop such attacks in ACAI, we ensure exclusive device ownership using the RMM. So when the realm VM is created and the device is attached to it, the RMM checks that no such overlapping mappings of the devices exist. That said, we still need to establish unforgeable identities with attestation and do some form of hardware-based encryption on the PCIe bus to protect against physical attackers. To do that, we use, for both encryption and for identity, we use PCIe 5's encryption capabilities. And how we do that and how it all comes together is pretty involved. So in the interest of time, I refer you to the paper for more details on that. To implement ACAI, there is no ARM CCA hardware yet, but there is an ARM simulator that has these extensions in it. So we build ACAI on this simulator, but the simulator has a problem. It does not have PCIe device support of any kind. So we had to build an escape mechanism that goes from the simulator to the host and talks to a real device that's connected to the host. Now, the FVP is instruction accurate, so as a best effort, we build a performance evaluation prototype on an ARM board to estimate its performance. We show that ACAI's changes are limited to the RMM trusted firmware and the guest Linux kernel, and we can run unmodified applications, drivers, and runtimes. We evaluate ACAI on a GPU and an FPGA, and we measure the number of instructions executed on the simulator as our performance metric. For the GPU, we execute a standard Rodinia benchmark suite, and for the FPGA, we use custom benchmarks. We compare ACAI against a baseline that uses bounce buffers with encryption, and here you can see the results of removing these encryptions from the workload. So on the x-axis here is the Rodinia benchmark suite, and on the y-axis is the number of instructions executed on the simulator on the log scale. So smaller is better, and the yellow bar, the orange bar is ACAI, and the blue bar is the encryption baseline. And we see that on average, ACAI gets about 26 times faster by removing this encryption. And also we see a correlation between the amount of data transferred and the gains that we get from this encryption by removing this encryption. So for backprop and SRAD v2 that transfer the most amount of data, we see the most gains of 47 and 44x respectively. And for SRAD v1 and NN that transfer the least amount of data, these gains are much smaller. For our FPGA benchmarks, we see a similar correlation between the amount of data transferred and the gains from removing encryption. Now, we break down the costs across different stages of execution for each of our benchmarks. Here, I take one example of SVD on the FPGA. Basically, there are 4 stages of execution: the initialization, host-to-device, and device-to-host data transfers, and the execution phase. And as expected, we see the most gains for the host-to-device and device-to-host data transfers, because that's when the data is moving and the cost of encryption shows up. We also see that the effect of ACAI on normal world execution is quite minimal, or on an average 3.8 and 1.9% for GPU and FPGA benchmarks, shown by these gray bars here. Now, as I said earlier, the FVP is instruction accurate, but not cycle accurate. So as a best effort, we micro-benchmark the costs of certain operations like context switches, interface calls, and memory protection. We also measure the costs of encrypting data using a standard encryption library that uses fast hardware encryption on this board. We then use these micro-benchmarks to estimate the performance of this bounce buffer setup and ACAI. And even with this very fast hardware-based encryption, we see that ACAI is 2 orders of magnitude faster. So in conclusion, ACAI aims to answer this research question on how to extend confidential computing to devices. In answering this question, we showcase the challenges that are involved and build a concrete design for CCA. In addition, we add device support to our simulator. All of our code is open source on GitHub, and we hope that benefits the larger community. Thank you.